My name is Sunaina Rane, and I'm a senior at Interlake High School in Bellevue, Washington. About 6 months ago, I found myself asking the question, how do galaxies form? Now, it's a simple enough question, and you'd think as a scientific community, with all that we've found out about the universe, we would know the answer, but surprisingly enough, we're not quite sure. You see, there are spiral galaxies, like our own Milky Way, and then there are elliptical galaxies, which look very different. They're like these luminous ellipsoids in the sky, and we still don't know how they could have formed. Elliptical galaxies have much less gas and dust than spiral galaxies, so one prevalent theory for how elliptical galaxies could have formed was that they would form from the merger of two spiral galaxies, which would result in a lot of fast loss of gas and dust, and that would result in an elliptical galaxy. However, recently, data collected by Dr. Jessica Rosenberg and her research team at George Mason University demonstrates that the amount of gas and dust in spiral galaxies before and after the merger is about the same. So this data would seem to disprove the theory that elliptical galaxies form from the merger of two spiral galaxies, or at least suggest that there's more to it. Now, I was fortunate enough to hear about this because I was at a talk given by Dr. Jessica Rosenberg about her research at the Summer Science Program, where I was a student doing research. Dr. Rosenberg was kind enough to talk to me afterwards because I had so many questions. And I was very curious about why we didn't have more theories about how elliptical galaxies could have formed. And in fact, one of the problems that she mentioned was that astronomers simply did not have enough data to support their theories about the formation of elliptical galaxies. So I sat there and went, how is that right? Because I know that there are so many publicly available astronomy data sets out there, and I know that there are telescopes and sky surveys constantly collecting data in the modern world. So a lack of data being a problem in astronomy never really occurred to me, until I found out that although there is all this data, very little of that data is actually labeled. So very little of it is directly usable to form new theories about things like galaxy formation. For example, researchers can't just pull up thousands and thousands of images of elliptical galaxies and their corresponding data and statistics and characteristics, because although those images are there, nobody knows that they are actually of elliptical galaxies. Nobody knows that data corresponds to an elliptical galaxy. It is just all in this huge data dump collected by astronomy data surveys. So I decided to design a research project in order to solve this problem by labeling these data sets, labeling galaxies as either elliptical or spiral, and automating this so that astronomers wouldn't have to spend hours and hours of skilled work time to try to create their two data sets. The idea was, with larger data sets that they could work with, astronomers would be able to formulate new theories, prove themselves wrong faster if that was the case, if their theories didn't work out, and to perhaps prove themselves right as well, and support their theories with hard facts, so that we could actually make progress in big questions like galaxy formation and other questions that really ask about how the universe got to be where it is today. Because galaxy formation really just is the tip of the iceberg when we start asking these big questions like, how did we get here? What are we doing here? Why are we here? Those questions that lead to the capital T truth that we all spend so much time looking for. And that search for the capital T truth really is the heart of astronomy and physics and just science, really, and is what thrills me so much about being involved in scientific research, that I'm contributing to finding the actual truth about why we're here, how we got here. The idea was also that I would create a tool that could be used on many astronomy data sets, or at least create a methodology of automatic classification that could be used on a lot of astronomy data sets so that we could start answering a lot of these different big deal questions about the universe and about how we got to be where we are today. So I started my research by finding an appropriate question, doing a literature survey, finding out a little more about what work had been done at the time, and reaching out to professors all across the world to ask if they would be willing to mentor me through this process, because I was very new to research at that point. I had just completed one astronomy research project. And I was astonished by the kindness of the scientific community, both of professors and of undergraduate and graduate students, in helping me throughout my research. Although virtual mentorship was difficult, but in the end, I think it worked out for the best. My research became more self-directed, and whatever feedback I did get was really, really useful and really showed me how collaborative the scientific community was. To this day, even after being named an Intel STS semifinalist, I have yet to meet any of my mentors in person, and I did all my research from home with my own materials because I was just really, really curious about this question, and it really showed me how research could be conducted and was accessible to even high school students with just a laptop at home. So I got this research question and I began developing models for galaxy classification. So this involved writing SQL queries for extracting data from the Sloan Digital Sky Survey data archives using the CASJobs interface. So I extracted multiple data sets and I started building models on each, and I tuned parameters for each model, like the depth of decision trees or the learning rate of a neural network, and I tried to see which model was the best fit, which model actually predicted what kind of galaxy, the type of galaxy, the best. And this required a really extensive, wide survey of the different types of algorithms that I could use and design. And then once I isolated the few that worked really well, a really in-depth tuning of those models to see how their performance could be enhanced. So before conducting this research, I really wasn't sure whether I wanted to go into computer science or physics or astronomy, and I always thought of these as separate fields with their own separate jobs. But throughout the course of this project, I discovered how truly interdisciplinary science is, and that I didn't necessarily have to choose, that there were research questions and projects and careers out there just answering questions like these about how do elliptical galaxies form, that combined physics, astronomy, computer science, math, and all the other good things in life. So I really found a direction in which I would like to take my future career, my future studies, and my future research. And I found out that I didn't have to give up on any of the good things in life. And in fact, combining them might yield the best solution when trying to solve hard questions and when conducting research. So there are many, many potential applications of this work in the future. That's the most exciting part, I think, for the work that I've done, is that researchers can go download this tool, the software tool that I've built from GitHub right now, online, and download the data sets that I've used, or create their own data sets and extract other data sets from public surveys, and with very, very minor adjustments to code, can use the same code to classify other data sets of galaxies, and can use very similar code to classify other astronomy data sets altogether that have nothing to do with galaxies or galaxy formation. And this very research project, just galaxy classification, can also be taken one step further, which I'd like to do by expanding the classifications, not just to elliptical or spiral, but also all the different in-between types of galaxies, the irregulars, the lenticulars, and barred versus not barred spiral galaxies. So this project was based on the Hubble tuning forward classification diagram, and there are many more stops on that diagram, many more subsections of elliptical versus spiral galaxies. We can definitely build models to have a little more predictive power and to make at least a guess as to which subtype of galaxy the data was coming from. One part of this research that's really close to my heart is that I would not have been able to build my models without some amount of training data, and that training data actually came from volunteers, students in classrooms, teachers who took their classrooms to go help research efforts, volunteers who actually went through and labeled their galaxies as elliptical or spiral or something in between. So this provided the base data set of about 600,000 records, for which I could train a model that would then go on to score millions and millions of data, millions and millions of images. And I hope that my work will similarly make a difference for astronomers who are studying galaxy formation and other astronomy problems, and who are trying to answer those big deal questions about why we're here, how we got here, and where we go from here.